2 problems. Yeah. Good. Okay. Well, let's go ahead and get started. Just to remind you of where we left off last time, our goal is to compute the basic observables in a quantum field theory, which are the correlation functions of a bunch of fields. And in this class, and probably for the next class or two, we'll just restrict our attention to the simple case where we have a scalar field that I'll call phi, only one of them. And that means that we would want to compute the expectation value of a bunch of phis multiplied together. Schematically, you could think about this as the amplitude for, say, a particle to be created at x1 and then absorbed at x2, and another particle to be created at x3 and absorbed at x4, and so on and so forth. And as we learned last time, the path integral approach naturally computes us the time-ordered expectation values, where we order, which is to say, the expectation value of a time-ordered product of the field operators, where the later operators are all ordered to be on the left, and the earlier operators are all ordered to be on the right. Now, if you were interested in particle physics, for example, you would not want to compute not just a correlation function, but something like, say, a scattering amplitude for 2 particles to scatter together and produce some other particle, or a decay rate for one kind of particle to decay into another sort of particle. These are all things that we can extract from this basic correlation function. And later on in this course, that is exactly what we will do. But for the time being, we're just going to content ourselves with calculating these correlation functions. So they're calculated in the path integral language by doing an integral over all possible field configurations. So I've called it an integral d phi, where the capital D reminds us that we're doing a path integral over all possible field configurations that this phi could take, including those that violate the equations of motion. And to compute this expectation value, we just insert a bunch of these phis into our path integral. And the technique that we used last time to begin computing these is we defined something that's called the generating function, or perhaps more properly, the generating functional, because it depends on another function that we called j, which is referred to as a source for particles. And z of j is simply defined to be the field theory path integral with the insertion of an additional term that couples j to our field phi. And then the idea is that our correlation function is computed by taking a bunch of variational derivatives of our partition function or generating functions with respect to the source j, and then evaluating those derivatives at j equals to 0. So are there any questions on this? So this is the basic setup, which we introduced last time. I'll just make a couple comments by way of reminding you of how you should think about this. If we were talking about electromagnetism rather than just a real scalar field, then the analog of this source term would be the term in the electromagnetic action that couples the electromagnetic field to some background source. And in this case, the source would describe some configuration of charge density and current density, so some 4-vector j mu. And what we're computing here then is the partition function z as a function of some background currents and sources. So you imagine inserting some currents and sources that you just hold fixed, and then summing over all possible values of the Maxwell field in the presence of those sources, and then weighting that sum, that integral, by the Maxwell action, including the source term a mu j mu. And here we just have a scalar field, so there's no extra indices floating around, so it's just j times phi. But as you can see, we could certainly generalize this to particles with spin or with a vector index or something like that. So then our goal is to go ahead and either compute z of j exactly if we can, or if not, if that's impossible, develop some sort of approximation techniques which will allow us to compute z approximately. Any questions before I continue? Yes?
So, when we evaluate the function z, we have to take j to 0.
At the end of the day, you're setting j to 0.
So
Yeah.
what does this mean?
Good. So what you should think about this is you should just imagine, say, expanding z in powers of j. So you would get 1 plus the I times the integral of j of x, phi of x dx, plus dot, dot, dot. Okay. So then if you look, for example, at the term that's linear in j, what does that thing include in it? Well, it includes in it all of the terms that look like integral d phi e to the is of phi of x. So if you wanted to compute the one-point function of phi, the expectation value of phi of x, then the way that you would do that is you would compute z to first order in j. And if you have a function and you want to compute, if you have a function of j and you want to compute the order j to the first power term, one way of doing that is you take the derivative of the function with respect to j and set j equals to 0. That's all these variational derivatives do, is they pick out the pieces. These variational derivatives pick out the pieces that are order n in j, because you're computing an n-point function, by taking n derivatives and then setting the j's equal to 0. Is that, hopefully that's more or less clear? Any questions on that? That's sort of an important point. Good. Okay. So what we did last time is we computed this in a free quantum field theory. And in particular, what we found is that this z, remember this z is a function of an arbitrary function j of x. So it's not a function just of a number j, but of another arbitrary function j of x. So it's what we often call a functional. And it's what we sometimes call, so very often the functionals that you've met so far in your life, things like the action is a functional of the path. That's what we would call a local functional because it was an integral d4x of something. This partition function is what you might call a bilocal functional because it's a function of two variables, x and y. And the quantity that you use to pair those x and y points together is the propagator. So it was the Feynman propagator or the free field propagator, whose form we wrote down explicitly last class and also several times earlier this semester. It has a very nice form in momentum space, which I actually won't bother to even write down right now. But it was that integral d4k of I over k squared minus m squared. Essentially, the way that you think about the derivation of this is that you think of that propagator as the inverse of the kinetic term. And roughly speaking, the calculation that you're doing is z of j is the integral d phi of e to the, well, integral of phi times some kinetic operator times phi plus phi times j. I'm being a little schematic here. And then that's a Gaussian integral. And the answer for a Gaussian integral like that is e to the j times d squared plus m squared inverse times j. And here, if I really want to take that equation seriously, I mean inverse in the sense of an operator acting on functions, and that the inverse of, say, the Laplacian is the Green's function for the Laplacian, or the propagator for the Laplacian. So this is a sort of schematic derivation, and the precise derivation is the one that we did last time. One of the things that you're doing on your problem set for tomorrow is you're working all of this out very explicitly for finite matrices, okay, where you can do exactly this integral, and you'll see that this is precisely the sort of answer that you get. There are actually some interesting additional terms that you'll find for finite dimensional matrices. The Jacobian determinant will appear somewhere. These actually also appear in quantum field theory, and they're very important, but for the time being, I'm not going to talk about them. Okay, any questions on this? So this answer that we wrote down for the free field partition function can actually be expressed very compactly if we use a diagrammatic notation. So in particular, the notation that we introduced last time is that we introduced a notation where you had a black dot for every term that was an integral d4x j of x. And every time you had a line between 2 points, say x and y, that gave you a propagator. And then with this notation, z of j was just the exponential of 1/2 times the simple diagram where you have those two dots connected by a line.
Put -1/2.
Oh yeah, sorry, I think actually, I'm not sure if I made a minus. So when I looked in my notes again, I did have +1/2. So sorry, I think I might have made a minus sign mistake last time. I'm pretty sure the answer is +1/2. It's always possible that when I did this, worked this all out, in my head I was using the wrong sign, but I'm pretty sure there's a +1/2. So yes, sorry about that. Good. Other questions? I think it had to do with there were a couple of i's that I hadn't gotten quite straight last time. Unfortunately, the subject is rife with factors of I and minus signs and things like that. But I don't want to get too caught up in those factors right now. Okay. So all of this is really quite straightforward. And in fact, it turns out that it's very easy to generalize this, at least in principle, to interacting quantum field theory. In particular, you could certainly imagine that we have a field theory where now, instead of just the free theory, whose kinetic term is quadratic in phi, you have some interaction term that is higher order in phi. So just for the sake of simplicity, let's just consider the case where you have an interaction term which is cubic in phi. So I'll call the constant in front of phi cubed g. I'll include a factor of 1/3 factorial for reasons that will hopefully become clear later on in this class. That's just a definition. That's just a notation of what I mean by g. And at least in principle, one could imagine going ahead and computing the correlation functions by now precisely performing this path integral, including this phi cubed term in the action. Unfortunately, I really don't know how to do any integrals aside from Gaussian integrals. And when talking about path integrals, we really don't know how to precisely do path integrals in any mathematically rigorous sense for when you have interaction terms of this sort. But what we can do is develop a systematic approximation scheme which will be valid when that coupling constant g is taken to be small. Okay. So the exact path integral, which you would need to compute the correlation functions precisely, is too difficult to do. But what we can do is make an approximation where this coupling constant g is small, and hopefully come up with some sort of systematic perturbation theory where we view this interaction term as a small perturbation of the free theory. I will make one comment, which is that there is a very rich subject of what's called lattice quantum field theory, or numerical quantum field theory, where people take integrals that they can't do exactly, such as path integrals of this sort, and they develop numerical techniques for studying them. And for studying quantum field theories without any small coupling constants, this is really one of the best ways to proceed. So, for example, one of the famous quantum field theories without any small coupling constants is quantum chromodynamics at low energy, the theory of nuclear matter at low energy. And a lot of the most important insights into that theory arise precisely because people essentially do this path integral that we're discussing, but they do it numerically. And there's an entire field devoted to the numerical computation of integrals of this sort. Similarly, for example, the quantum field theory that governs the three-dimensional Ising model, one of the famous statistical mechanics systems, when you're near a phase transition, also involves a path integral of this sort, but with coupling constants that are finite rather than small. And in this case, again, a lot of the data that we have about this theory comes from numerics rather than from this perturbative expansion that I'll be developing momentarily. So, how would we imagine computing this path integral? So, this path integral z of j, when g is very small. So what is that? I'll just write it down for you. So it's an integral d phi of the exponential of I times the integral d4x of our free Lagrangian. So I'll just call that L free. So that's L free right there. Plus the interaction term plus our coupling term j of phi. So let's just imagine trying to compute that for our simple phi cubed interaction that we have up here. So what is that? Well, let's just imagine taking that L interaction term, so you have an e to the I integral of that interaction term. And you have this constant here which is small. So let's just imagine expanding that exponential in a Taylor series. So this would be an integral d phi of e to the I times, well, let's just call it integral of L free plus j phi. And then we'll take that e to the I integral of L, and we'll just expand it out in a Taylor series. So you'll get 1 plus ig over 3 factorial times the integral d4x of phi of x cubed plus higher order terms. Well, of course, that leading term there, we know how to compute. Okay. That's just the term in the free theory where g is set equal to 0. But what's that linear term? Well, that linear term just involves an insertion of 3 phi's in our path integral. And you know how to insert phi's into your path integral. You take a derivative with respect to j. So what is that? You could write that as 1 plus ig over 3 factorial times the integral d4x of the derivative with respect to j of x cubed, acting on the partition function or the generating function of the free theory. So I'm just reusing the computation that we did above, where we noticed that if you want to insert a bunch of phi's in the free theory, you just take the variational derivative with respect to j. Or if I wanted to write this out a little bit more systematically, you could write this as not 1 plus ig over 3 factorial, etc., but you could rather resum the exponential. And what would you get? You would get the exponential of I times the integral d4x times, well, the interaction term, but with phi, not the interaction term as a function of phi. Here, let me just write it out explicitly for this phi cubed case. But the interaction term with phi replaced by a variational derivative. So you would get integral d4x times g over 3 factorial times d by dj of x. Oh, and I'm sorry, I forgot there should be a factor of minus I here, right? Because every time, because j, there's an I multiply, it's I j phi, so you need a 1 over I in order to bring down a field. Okay. Right, that's just this, this factor of minus I right here. Good. So you have a minus I times this variational derivative cubed. And all of that is the variational derivative of the answer for the free theory. But we already computed the answer for the free theory. What is it? It's the exponential of this guy that involved 2 propagators, of j of x, delta of x minus y, j of y. Okay. Is that clear, more or less? I haven't really done very much except use things that we already learned, namely that if you want to insert a bunch of phi's in this path integral, you take a variational derivative. Is that clear? Is everyone more or less clear? Now, this is still a very complicated beast to compute. And this is not something in general that we'll even try to compute exactly. The important point is that I can now expand this out to any desired order in G that you like. In particular, what I'd like to do is I'd like to imagine expanding out the exponential. So what I'll do is I'll take this exponential and I'll expand it out. So I get a sum over an integer, I'll call that integer v, of 1 over v factorial times the quantity being exponentiated. So you get an I g over 3 factorial times an integral d4x of minus I d by dj cubed, all to the v power. And then while we're at it, let's expand out that second exponential as well. So I'll write that as a sum over p to infinity of 1 over p factorial. So here p is just another integer of 1/2 times an integral. You know, just to keep things clear, maybe I won't call, I really shouldn't call that x and that x, because they're both just variables that I integrate over. And so just to emphasize the fact that they're different, I'll call these variables y and z. So you have a j of y, delta of y minus z, j of z. And there you have it. There you have an expansion of the generating function in terms of these two parameters that I've called p and v. And the basic idea is that if we want to compute an answer, to some desired order in our perturbative parameter g, our coupling constant g. So let's say you only care about something that's of order g to the n. So if g is a small parameter, then that would be a good approximation if n is large. Then we only include terms with v less than or equal to n. Similarly, if we are computing, say, an endpoint function for some number, a correlation function of some number little n of phi's, then we only need terms with p less than or equal to little n. Oh, I'm sorry, to the p power. Thank you. Good. Right. Sorry about that. Right? Because the only way that you ever get, so if you want to compute, say, a 4-point function, phi at x1, phi at x2, phi at x3, phi at x4, then you need to take this partition function and expand it to fourth order in j. And the only terms that you'll get that are fourth order in j or lower order in j will come from the terms where p is equal to, p is less than n over 2 here. And I get, right, because you get 2 powers of j every time you increase p. So for example, if you want to compute a 4-point function, you only need the p equals 0, p equals 1, and p equals 2 terms. And if you only care about that answer to order g to the third, then you only need to keep the terms where v is less than or equal to 0, 1, where v is 0, 1, 2, or 3. Okay. Now, so far I've written what looks like a kind of very complicated, non-intuitive expression for this generating function. But the point, and the thing that makes this such a nice way of organizing our thinking about the theory, is that each of these terms in Z is represented by a diagram and it's a diagram with V vertices and P lines. And the rule is that each vertex will connect 3 lines and is associated with a power of g. So it connects 3 lines, but it comes with a factor of g. And similarly, each of these lines, so you have p lines, and each line is associated with a propagator. So each line comes with a propagator. And the total number of powers of j in one of these terms, what is that? Well, let's imagine expanding out this expression here for z. Well, let's look at a term with some v and some p. For each p, you get 2 of those j's, but for each v, you lose 3 of the j's. So the total number of j's is something that we could call E, and it's 2p minus 3v. Okay. And this is the number of external sources, the number of powers of j. So just to summarize, the rules completely explicitly, what we have is that this partition function is a sum of diagrams built out of the following ingredients. So you have some number of external sources that are represented by a solid dot with a line. And for every external source, you write down a factor that looks like the integral d4x j of x. Every time you have v vertices that you use to connect up these propagators, so these external dots, which has each of which comes with a factor of g and an integral d4x. And you have p lines, which are usually called propagators, each of which gives you a factor of delta. And there are sort of, if you like, you could label positions associated with these endpoints. So, for example, there would be a position there, and 2 positions associated with each propagator. And so this gives you a completely explicit and sort of geometrically intuitive way of understanding how to compute this path integral. And really all we've done here, I mean, it's sort of useful just to sit and stare at this. This is kind of an amazing formula here. It's just useful to sit and stare at that formula for a second. And you can see that as you expand, every time, so let's just imagine expanding out this integral here first. So let's imagine doing this at order v to the 0. So doing the v equals 0 term. So if you did the v equals 0 term, that's just like setting g equals to 0, and you get the free answer. Okay, you get 1 plus a half times that, so if you times you just get the free answer. 1 plus a half times, 2 dots connected like that, plus 1 over 2 factorial times a fourth times this guy squared, and so on and so forth. But then, once you start including powers of j, you're allowed to take derivatives with respect. Once you start including powers of g, you're allowed to take derivatives with respect to j. What does that do? That removes those dots. And in particular, it removes 3 of those dots. And it allows you to connect the lines together. Right? I just want you to convince yourselves of that for a second. Like, let's imagine taking, say, a term here with some number of powers of j. Let's say you have j of x1 delta x1 minus x2 times j of x2 times a bunch of other j's, let's say you've got 12 j's there, I don't know, then if you have a term there that would come from including the effect of this coupling constant g, then you take 3 derivatives with respect to j. That allows you to remove 3 of those dots and connect those lines together. Is this clear, more or less? It might be helpful just to start using these rules to write out the Feynman diagram expansion of this generating function. So for example, let's imagine that we wanted to compute at e is equal to 0. So e is equal to 0 means we want to compute the terms in the partition function with no external sources. So these are sometimes referred to as vacuum diagrams. Or also sometimes referred to as bubble diagrams. So what would these terms look like? Well, you could just imagine starting with trying to construct, using these 3 rules, diagrams, using those 3 basic building blocks, diagrams with no external vertices. Well, the first thing you see, well, p and v are both positive integers, or non-negative integers, I guess I should say. And if e is equal to 0, that means that 2p is equal to 3v. Okay. So the first thing that you could write down would be the case where v is equal to 2 and p is equal to 3. Right? Because you need 2p minus 3v is equal to 0. And what sort of diagrams could you write down with v is equal to 2 and p is equal to 3? Well, v is the number of vertices, and p is the number of propagators. And so the 2 contributions you get to the partition function look like that and that. So if you want to compute this partition function, the generating function at order j to the 0, so you want to compute this guy without any external sources, and you only want to compute it to order g squared, where g is the coupling, then these are the only 2 diagrams you need to compute. And what are these diagrams? Well, we can write down the formula associated with each diagram just by using the rules that I have developed up here. So what are they? Well, it's an integral. This one is an integral d4x times an integral d4y with 2 powers of the coupling, and you get a delta of xx, delta of xy, and delta of yy. We're here, delta xy is the propagator between the point x and the point y. I suppose really, when I write the propagator, I've been writing it as a function of x minus y because I'm using the fact that there's translation invariance. So really, I should call that actually delta of 0, delta of x minus y, and delta of 0. Okay. That actually would be a more correct way of saying it. I'll write it that way. Good. And what is this guy? Well, that is an integral d4x, integral d4y, times delta of x minus y cubed. Sorry, now that I erased this thing, it looks sort of funny. So that's supposed to go there. Now, if you wanted to work, let's say you wanted to compute this guy at higher order. So if you wanted to try and compute this guy at order g cubed, then that would mean you were looking for terms with v is equal to 3. But I challenge you to try and find a value of p such that if v is equal to 3, e is equal to 0. Okay. You can't do it because 9 is an odd number. So the next contributions will come when v is equal to 4. That is to say, at order g to the 4th. So these would be the order g squared contributions. The order g to the 4th contributions would have v is equal to 4 and p is equal to 6. And so you then go ahead and try and write down all of the possible diagrams that you can with 4 vertices, each of which connects 3 different lines, and 6 total lines connecting them. Okay. So you can just sort of, once you get the hang of it, it's really not hard to find them. Okay, I didn't draw that very well. But it's just 3 loops connected by 2 propagators. You can see there are 6 lines there. There's going to be another one where you just take this diagram here and you insert another line. Then there'll be another one where you take this diagram that we wrote above, and then you take another line that connects them. There'll be another diagram, that looks like this. And then finally, there'll be either the peace symbol or the Mercedes symbol. I never quite remember which it is. Did I miss any? Are there any other diagrams that will occur at order g to the 4th? And using the rules that I wrote down above, you can now just write down a formula for each one of these diagrams. Okay? When we write down Feynman diagrams, we're not just drawing pretty pictures, we're writing down formulas. But it's a very simple way of writing down formulas where you don't have to keep track of all the integrals and stuff like that. Now, so far I've just been computing the vacuum diagrams. Let's imagine that you wanted to compute the diagrams with one external leg. So if you want to compute the diagrams with one external leg, so remember that E is equal to 2p minus 3v. So the first case where you could have E is equal to 1 would be when you have one vertex and one propagator. So what does that diagram look like? Well, it looks like that. It's what's sometimes known as the tadpole diagram. People often give, sort of melodramatic names to these diagrams. So this is what's known as a tadpole diagram, because it looks a little bit like a tadpole, I guess. So this would be the contribution to the 1-point function at order g. There are no contributions at order g squared, because there are no diagrams that you can write down. There are contributions at g cubed. So if you want a 1-point function at order g cubed, then that means v is 3, so p must be equal to 4. So that, sorry, did I get a minus sign? Is this minus e? I guess this is minus e, isn't it? Thank you. So, why am I saying thank you? Well, I guess I could thank myself for correcting a typo. Usually I have to thank other people. I'm just so used to other people catching my typos that I automatically thank whoever catches it. Good. Good. So, so what are the diagrams that compute at order g cubed? Well, there's the one that you get by just adding an additional line to the tadpole diagram that we had above. There's one that comes from adding another tadpole to the tadpole that we had above. And then there's one other diagram where we take these two tadpoles and we sort of connect their tails together. and so on and so forth. And you can quickly see that if you work at higher order in the coupling, the number of diagrams will very rapidly proliferate. Question?
Can we look back at how we derived E equals 2P minus 3B?
Yes. I think I made a sign list. I think it's
Yeah, but even from the equation I had.
right. Good.
We have our negative 3B coming from the
Mm-hmm.
sum or
Right. So the number of external vertices is the number of. Sorry. Okay. No. Yeah. The number of powers of j that you have here. Every time you have a p, you get 2 j's,
Yeah.
and every time you have a v, you lose 3 j's.
Yeah.
That's the.
Right, but that's what's kind of confusing to me because
Yeah.
that still gives us the E equals 2P minus
Yes.
3B.
The point is that. Yeah.
We can work with the E equals 1 that we just made. Like you
Sorry.
would make me think, oh, we can have 2 propagators and 1 vertex.
Yeah, I guess I'm being sorry. I guess I didn't do that counting quite right. If you want E is equal to 1, and you really, sorry, I guess what I need here, I was being a little sloppy. You need to include that guy there as a propagator, right? And you need to include, so, sorry, I was being a little sloppy. My apologies. This is the problem with teaching a class at the end of the day. So those all count as propagators. Good. Sorry about that. Yeah. This is what happens when I slavishly follow my notes. Okay, no typo. No thank you for me. Good. Sorry about that. Good question. Any other questions? Yes.
What about the three factor?
Good. We're going to get to the numerical factor in just a second. Okay. So indeed, right now I'm writing down the equations, but there's some combinatorial factor out front that we're going to have to keep track of. And that is a little tricky, so I'm going to defer that for just a minute. Yes?
When we are using path integral technique for computing working energy,
Mhm.
it was like the sum over all path will start from somewhere and end somewhere. And here we are like having the partition sum that looks like it's the sum over like everything what can possibly happen in variables.
That's right.
And,
That's right. I mean, you should think, you should really have pictures in your head associated with these diagrams, right? I mean, I think that is the right thing to think about. You really can think about these diagrams as particles moving around and interacting with one another. Like let's take this diagram here. Like what is this term represent? Well, it represents, say, a particle that is created at a position x and is destroyed at a position y, and this interaction term really is allowing these 3 particles to interact at a point x. Sorry, maybe I should say that a little differently. Each of these propagators represents the amplitude for a particle to travel from x to y, and the interaction vertex allows 3 particles to come together at a point and disappear. Or alternatively, you could think of it as allowing 1 particle to come and create 2 other particles. And so this contribution you can really think of as, particles that start at x and end at y, and they sort of all come together in the way that's described by this diagram. Things get a little bit clearer if you think about more complicated interactions. So for example, if you want to study E is equal to 2, then the simplest term has V equals 0, and P is equal to 1. What is that term? Well, that's the term that we've met already. It's this term right here. That's order G to the 0. There are no terms at order G to the first power because V comes with an odd number in front of it. So the next term happens at V is equal to 2. And if V is equal to 2, P is equal to 4. So what sort of diagrams would you have? Well, you would have a diagram like that, and a diagram like that. So this is some diagram that would contribute at order g squared, and then you would have more diagrams at higher order. And there's really a story that you can tell yourself when you write down diagrams like this. Because what did this diagram represent? Remember, this is the diagram that was present in the free theory. And it represented, say, a particle that was born at position x and died at position y. And it's the contribution to the partition function was this propagator that described the amplitude for a particle to be born at x and die at y, if x happens before y. And if x happens after y, it's the probability or amplitude for a particle to be born at y and die at x. And then what is the story that you tell yourself when you write down that diagram? Well, it's the amplitude for a particle that's born at x, and then at some intermediate time z, it splits into two particles that recombine at some other intermediate time w before the particle dies at y. And for example, if you were imagining some higher order diagram, you could associate a more complicated process, say, like that. That would describe a particle that is born at x, splits apart at z, at, some other times w, and I'm going to run out of letters, r. Each of those particles, a particle gets emitted by r, and then it gets absorbed by one of the other particles at w, and then at some other time s, they all recombine before finally forming a single particle that dies at y, and so on and so forth. And in the same way that when we write down the path integral, you really think about summing over paths, configurations that don't solve the equations of motion. All of the particles that participate in the story that we're telling ourselves when we write down this diagram are particles that are not traveling that are not obeying the equations of motion. They're often what are known as virtual particles. They're called virtual because we never actually observe them. Remember, the thing that we observe is the thing in the correlation function. And the thing in the correlation function, all you know is that a particle is born at x and it dies at y. You don't know what happens in the intervening time. And just as in the double slit experiment, different paths that a single particle can take through the two slits can interfere with one another. Different stories as told by different Feynman diagrams will interfere with one another. And so there will be all sorts of complicated effects that can arise because of that. So the derivation of Feynman diagrams using this path integral is really very slick. I mean, it's almost too slick. Like, I went through it. You can do it very, very quickly. So it's important to really understand this derivation in a fair amount of detail. So for example, the problem set I just handed out, you're going to derive the Feynman diagrams that you use to compute not an infinite dimensional path integral, but a one-dimensional integral. We've introduced Feynman diagrams as a way of approximating integrals, and there's no point in wasting them just on infinite dimensional field theory path integrals. Normal one-dimensional integrals can be approximated using this Feynman diagram technique. And so in one of the problems that you'll do this week, you'll beat to death a simple simple one-dimensional integral. You'll do it numerically, and then you use Feynman diagrams to understand how they give you a successive approximations to the answer. And along the way, you'll understand some kind of important subtle issues about this Feynman diagram expansion. Good. Any questions on this? Okay. So there's one final point, and it's a point that I hate discussing because it's really confusing. And it's the discussion about what numerical factor goes in front of each term in the Feynman diagram expansion. So the question that we want to ask really is, of the various terms that appeared in our expression for z as a sum over p and v, how many terms in the expansion of z of j that I wrote down above contribute to a given diagram? And we need to answer this question in order to compute this numerical coefficient. You know, we had this expression that we wrote down here for our generating function. And there's all sorts of combinatoric factors that will appear when you think about a given Feynman diagram. So a given possible structure of deltas and j's that you could write down that would contribute to this partition function. So what I want you to do is think about, say, a term in this generating function with p propagators and v vertices. Okay, so some p is fixed to be some number and v is fixed to be some number. Then for each value of v, you know, you get this 1 over 3 factorial here. But there are also those d by dj's that you have here act on various j's that appear later in this expression. And there are 3 factorial ways that you could rearrange those 3 j's. There are 3 factorial possible permutations of those d by dj's, and that's going to cancel this 1 over 3 factorial that appears here. You know, at order v squared, there would be 3 factorial times 3 factorial rearrangements of the j's, which will cancel the 1 over 3 factorial squared. Similarly, for each propagator, there's going to be 2, or maybe I could call it 2 factorial, different ways of rearranging the vertices in this propagator that will cancel that 1 over 2 to the p power here. Finally, there are going to be v vertices, and there are v factorial different rearrangements of those vertices, which is going to cancel that v factorial here. And there are p factorial rearrangements of the propagators, which will cancel the 1 over p factorial here. So if this is a little bit confusing to you, just imagine expanding this all out explicitly to get a term, like let's say that you wanted to expand this out to get this term here. Okay, that is to say to get this term here in z. Well, you have to think about all the possible different ways you could get that term in the expansion of z. Okay, and there's lots and lots and lots of different ways. Okay, why? Because there's all sorts of different ways that you could match up these d by dj's with all of the j's that appear when you expand out this term. There's 3 factorial for each vertex. And similarly, there's various different ways that you could match up these deltas with each one of those vertices. So maybe I can just restate that because, you know, it's a little bit subtle. But basically, there are 3 factorial permutations of the j's, or let's call it rearrangements of d by dj in d by dj cubed, which will cancel any factors of 1 over 3 factorial. And similarly, there are 2 rearrangements of, say, the j's in the j delta j, which will cancel the 1/2. And then similarly, there are v possible rearrangements of vertices, which will cancel the 1 over v factorial, or sorry, I should say they're v factorial rearrangements of vertices, which cancels the 1 over v factorial, and there are p factorial rearrangements of propagators, which cancels the 1 over p factorial. So what does that mean? That means that if the argument that I gave you up above were right, which unfortunately it's not, but if that argument were right, each term in each diagram has a coefficient, a numerical coefficient, that's precisely equals to 1. Because the combinatorics of all the different ways that you could find a given term in the expansion of z is precisely canceled by those combinatorial factors that appeared in the expansion of z. You know, that's why I introduced that 1 over 3 factorial when I defined the coupling constant g. The problem with this argument is that there are some cases where you can rearrange vertices or propagators and get the same diagram back again. So in order to make this just a little bit more precise, let me just introduce a definition. So let's say that a permutation of a diagram is a rearrangement of vertices, propagators, the 3 lines coming out of the propagator, of a vertex, or the 2 endpoints of a vertex. So, you know, we had 4 different objects that we needed to study the combinatorics of. And so what I want you to do is in your head is I want you to write down a given diagram, and then I want you to assign a little index to each one of the vertices and the propagators in this diagram. And then a permutation will, or introduce a little label, you know, color each vertex a different color if you like. And then a permutation will swap around all of these vertices. And then the number of symmetries of a diagram what is it? Well, it's the number of permutations that leave a diagram invariant. And that number of symmetries is precisely the amount by which we have overcounted the contribution to the generating function when we use that naive combinatoric argument up above. So we'll call the number of symmetries S sub d, and then each Feynman diagram must be multiplied by a combinatorial factor, which is 1 over the number of symmetries. This is sometimes known as the symmetry factor associated with a given Feynman diagram. The problem set that I just handed out will have you do 2 very simple examples of Feynman diagram calculations. And in both cases, in order to get the right answer, you'll need to get the symmetry factors right. In both cases, however, you will already know what the correct answer is because you will have done the calculation a different way. So those will be 2 cases where you get a lot of practice in calculating these symmetry factors. So let me just give you a couple examples. So let's take this guy, the barbell diagram. So what are the symmetries? Well, there's one symmetry that interchanges, it's a little hard to draw, that interchanges the two lines here coming out of that vertex. There's another symmetry that interchanges the two end lines here. And then there's one final symmetry that just sort of does the mirror reflection about that mirror right there. So the total symmetry factor of this diagram is 8 because it's the product of those three symmetries. So if you wanted to say it a little bit more systematically, the group of permutations of this diagram is generated by three reflections, or it's an order 8 group. Similarly, if you took, say, this diagram here, oops, sorry, that's a 5 to the 4 diagram. If you took that diagram here, what would you get? Well, the symmetry factor, there are 3 factorial. You get a 3 factorial because you got three propagators here that you could permute. And similarly, you get a factor of 2 because you can interchange the two vertices by doing a reflection. So the symmetry factor there would be 12. Any questions on that? Yes.
We can always exchange the two vertices, right?
Yeah.
Why don't we count for that already at the beginning of dividing by 2?
So maybe I'm not. What do you mean?
So whenever we have, okay, in this case, 2 vertices, even with more vertices, we have all the possible combination of the vertices.
Mm-hmm.
Why don't we count
So
at the beginning
that
as in the same way that
that's this 1 over v factorial. That's the thing that cancels that 1 over v factorial.
Yeah, exactly. So you said
So so if you let's say so that diagram was a term with v is equal to 2. So there's a 1 over 2 factorial, okay? And there are 2 different ways that you could interchange those two vertices. Okay? And so that, at least naively, canceled that 1 over 2 factorial. And similarly, there was a 1 over, I forget what p was. P was 3, I guess. And that canceled the 1 over 3 factorial. Except when I made that argument, I actually made a mistake because of the fact that, because this diagram had a symmetry, and so they didn't actually completely cancel it out. So in particular, this 2 arises precisely because I can't fully cancel out all of those combinatorial factors.
So maybe the question is, do we always get a factor of 1 whereas the factorial times
No, you don't. Yeah, I mean, but I've drawn down 2 symmetric, highly symmetric sorts of diagrams. But if you had diagrams with fewer symmetries, then you wouldn't get that. Like, so for example, it's a little, if you had this guy, then you wouldn't be able to interchange the 2 vertices. You wouldn't be able to interchange this vertex with this vertex, although you would be able to interchange that vertex with that vertex. Right.
when you talk about symmetry, you talk really about, it looks like you're talking about 3 dimensions. Like
I'm not quite exactly sure. What I mean, what I want to think of is you think of all of the various different ingredients that make up this diagram, the dots and the lines, and you think about maps of this diagram that take dots into dots and lines into lines. And then you ask how many of those maps don't do anything to the diagram. Yeah.
Yeah, similar question just regarding the symmetry where
Mhm.
you're flipping the propagator above and below the loop there.
Yeah.
Like, why isn't that
so remember that when you write down a propagator here, the points y and z are sort of treated separately. Okay? So this propagator remembers which 2 points it's connecting. And
It's just the fact
yeah,
that X and X could be exchanged.
right. It's the fact that those x's could be exchanged. It's a little, I mean, this is a sort of, let's put it this way. The subject of symmetry factors is a legendarily tricky subject. I've tried to, one of the reasons why I like this path integral derivation is that it makes it completely clear what the answer you're supposed to get should be. So if you're ever confused, so for example, this term here gave you something that was like integral d4x, d4y, delta of x minus y cubed. Okay? So all you need to do, if you don't want to think about symmetry factors, all you need to do is take this integral take the sum that we wrote down here, look at the term with v equals 2 and p equals 3, and just write down every term that appears. And you'll get a 1 over 2 factorial from here, a 1 over 3 factorial from here, a 1 over 3 factorial squared from there, was a 1 over 2 cubed from there. Okay, so you get some, I forget what that number is, but you'll get some big number in the denominator. But then you have all kinds of different terms that you need to add up. Okay. Yeah, maybe this would be a good thing for a problem set. But yeah, and so you'll get all sorts of terms here, and you'll have 3 d by dj's that will need to act on the other j's that you have, and you could just write it all down completely explicitly. Yes.
Like, I guess sameness or like symmetry is the integral you get at the end. Like if you wrote the integral and you change the labels all around, and the integral is the same, that's the symmetry.
Maybe yeah, exactly. No, I see what you mean. Yes, that's exactly right. Yeah. So, for example, one thing that's important to remember is that, you can always change variables in that integral, right? So, like, you'll write down many different terms that will all look like this term here, but you might have different names for those variables, but I don't care about the names for the variables, okay? You just need to, you'll just get a bunch of terms that all, if you do a change of variables, will be the same, okay? And then I just want to calculate the numerical coefficient. I mean, I don't want you to obsess too much about these symmetry factors. They're one of the things that are important, but kind of annoying. So, I think the important thing is that, well, the most important thing is that you understand where the Feynman diagram expansion comes from. Symmetry factors are the sort of thing where you find yourself having to compute a diagram, and every time you have to compute something, you have to sort of stare at it and sort of scratch your head for a while to sort of figure out the symmetry factor. But hopefully you'll get some practice with it at the problem set this week. Any more questions? Yes?
It's still about the symmetry factors. So I understand in the first diagram we can interchange the loop.
Mm-hmm.
But why did we do it for the second one for each one?
Well, so for this diagram, you can interchange. You can you can kind of interchange. If you like, you could change the orientation of the loop, if you want to think about it that way, and you can interchange the orientation of this loop. And so there's a total of 4 possible different orientation changes that you can make, which is why you got a 2 times 2 here. So you could do, say, change the first. You could not do anything. Or you could change the first and not the second, or the second and not the first, or you could do both. That gives you a 4. Then you also can swap the 2 loops. Okay, so that gives you this other factor of 2 here, because you could change the orientation of one and swap it with the other. And hopefully, if I've done it correctly, that gives you all of the symmetries. It's, yeah. Any more questions on this? Okay. There's more that I wanted to say. There's a lot more that I wanted to say. In particular, one of the things that I'll comment on, so I don't think I want to go through it this class because I'm almost out of time. But one of the things that I'll comment on, just very quickly, is the following, which is that when we computed these vacuum diagrams, for example, you're getting a contribution to z at j equals 0. And at the end of the day, remember, our instructions are to divide out by z at j is equal to 0. So all of the vacuum diagrams are going to end up canceling out. So what that means is that there are, in fact, improvements to these. So the Feynman rules that I've written down for you are perfectly correct. But what we'll do next time is we'll understand some improvements to these Feynman rules. Well, that will actually allow us to avoid calculating most of these diagrams. In particular, what you'll see is that all of these vacuum diagrams, unless one is interested in actually calculating the cosmological constant, will never actually matter in your theory. And similarly, these diagrams here, these diagrams contribute to the one-point function of phi, to the expectation value of phi in the vacuum state. And remember, our starting point in our study of interacting field theory was the declaration that if phi has a non-zero one-point function, a non-zero expectation value, you can always just shift phi to set that expectation value to 0. So similarly, we're always going to shift our value of phi so that these tadpole diagrams here aren't going to matter. Indeed, it's a pretty good thing that these vacuum diagrams and tadpole diagrams don't matter, because if you look at this expression that I wrote down here for a vacuum diagram, well, nobody commented on it, but you probably noticed that we had delta of 0 there. And remember that delta of 0, well, how does delta behave? It goes like 1 over x minus y to some power for a massless field. And so at 0, it blows up. The two-point function, phi of x, phi of y, has a singularity as x approaches y. So strictly speaking, those vacuum diagrams are infinite. And in fact, that divergence in the vacuum diagram is a divergence that you've met at least twice before in this class. That's the usual divergence in the vacuum energy. And so it can be ignored for exactly the same reasons as we've been ignoring it previously. So all of these contributions to the vacuum can just be interpreted as a shift in the energy of the ground state. Okay? They can be interpreted as a total so it's actually it's not entirely obvious at this point, but it'll be clear next class that all of the vacuum diagrams, you can sum up this infinite set of vacuum diagrams and interpret that as an overall shift in the ground state energy. And similarly, you can sum up all of these one-point diagrams and interpret that as a total shift in the vacuum expectation value of phi. And so we're going to go ahead and discuss how we remove those next time. And this is really a subject that gets into kind of the sort of notoriously tricky subject of infinities in quantum field theory. So when we start considering basically any loop diagram, you start getting these infinities. And we'll be developing this course a sort of more sophisticated understanding of what these infinities mean, when we can get rid of them, why we can get rid of them. But I just wanted to point out that they're there, because it would have been sort of unfair of me to write down these diagrams and pretend that they actually make sense. Okay. They do, but you just have to think about them a little bit before you try and interpret them. Right, like any of these diagrams, though, even like things like this, all of these diagrams diverge. Like all of these diagrams diverge. And so when we actually get to computing physical quantities, we actually are going to have to be a little bit more careful. Any questions before I end? Great. Okay, I'll see you next week.